Welcome to today's class where we're going to be talking about what is friction. Friction is a contact force that is resultant of two objects that are touching each other in contact with each other, trying to move and slide against each other. So let's say I have this block here, and actually we'll just make it on top of a table. This table, ignore the fact that it's rotated. Let me see if I can unrotate this. Yep, that looks good. If I were to try to push it this way, friction would oppose that motion and try going backwards. And that's going to be one of the first big ideas I talk about for friction, is that it opposes motion between two objects, or as it's more professionally called, relative motion. Now, this is an idea discussed at the end of Unit 1, relative motion, the motion between two objects. What's important to note is that all motion is relative. It's just that when we're discussing normal motion, we're speaking about it, well, we're normally discussing motion, we speak out more absolute terms, except it's still relative to one object. For example, when we're talking about the movement of someone, like walking, we're on a revolving planet. But we don't take into account the fact that the planet is revolving, because that would add a lot of velocity and motion to their movement. We only talk about their motion relative to the ground, to the surface of the earth, the point of earth that they're at. Instead of talking about their motion relative to this point in the universe, we're talking about their motion relative to this point on earth. And why is that important? Because friction resists specifically relative motion. If there is no motion relative between the two objects, then there is no friction. So, just for like a quick experiment to try this yourself, if you were to clasp your hands together, push them against each other, and try pushing one forward and pull the other back, you'll notice it's kind of hard to do due to the friction. But if you put them together and move both of them forwards, there's little to no resistance because friction isn't doing anything because there's no relative motion. Okay, now that we've discussed that, let's actually talk about how to calculate friction. Friction takes on two forms, kinetic and static friction. Kinetic friction is the easier of the two. And it's calculated solely as Fk, or Ff. Sometimes you even see Fr, although Fr is less common, equals negative mu Fn. Sometimes you won't see the negative sign. One of the challenges of friction is trying to figure out the direction yourself, because a lot of the times in physics classes, actually the forces aren't the direction of the forces aren't really defined that well. You can treat a force as having its own innate direction, like when you're writing sigma F equals like Fg plus Fr. In this case, Fr is a resistive force, and you would say Fr is negative, so this is intrinsically negative, or it's inherently negative. I don't know why I said intrinsically. Or sometimes you'll see Fg minus Fr, where Fr is held as a positive value that you're subtracting. You'll see both. I personally treat all of my forces as typically positive, and I just subtract or add them. You'll see both, though. Either way, this is saying the reason why we have it as negative is because it typically goes in the opposite direction. Well, because it opposes motion, it goes in the opposite direction of motion. So you're going to see it typically written as a negative value. So minus mu, this is mu, the Greek letter mu. Kind of looks like a U, except dragged down the sides. Fn, where Fn is normal force. And what's important to know is that this mu is also mu k. So you might want to note that this is mu k because kinetic friction and static friction have different values. And static friction is actually there's no equal signs. It's less than or equal to negative mu s Fn. So kinetic friction is the friction between two moving objects. Static friction is the motion between, well, is the force that's preventing any motion from starting between two objects. To better define it, kinetic friction is there when there's already a relative motion between two objects that are in contact with each other, while static friction is when there isn't any. It's when one of them is trying to move. So let's say you have a heavy box that you're pushing. You're pushing against this box. It hasn't started moving yet. When it hasn't started moving, so in stationary, there is an Fs, a static friction pushing against you. But once it does start moving, it's going to turn into Fk, kinetic friction. And what you'll notice is that it's easier to move it once it's already started moving. That's because the mu k, or the coefficient of friction as it's called, is lower than mu s. The coefficient of static friction is higher than the coefficient of kinetic friction, because when you have two objects and they're in constant motion against each other, there's not much time for the atoms to bond and really settle in. Once they're stationary, though, the atoms can really click together. I guess the easiest way to think about it is like Velcro or glue. Yeah, Velcro or glue is kind of the easiest way to think about it. With that analogy, I'll just stick with the glue right now. If you give time for the glue to solidify, then you'll notice it's a lot harder to move than if you're just pushing against it while the glue is still liquid. Now you also notice is that the Fs is less than or equal to negative mu s Fn. That's because static friction is intelligent. What do I mean by that? I mean it's only as high as it needs to be. Let's go back to this example. Let's say you are pushing against this box with 100 newtons of force. Okay? The coefficient of friction, let's say, is 0.6, and the Fn, the normal force, is 200. So now you're pushing against it with only 100 newtons of force. What you notice is that this total can reach a maximum of 120. The static friction is going to hit that limit of 120 when you're only pushing with 100 newtons of force, because if it were to go to 120, then it's going to start accelerating this direction because you're going to push 100 this way, there's 120 this way. So it's not going to be eliminating motion in that case, it's going to be causing motion. Remember, friction, its goal, I guess, is to eliminate relative motion. So it's only going to go as high as it needs to eliminate relative motion. So while you're pushing this way with 100 newtons, it's pushing back with an equal 100 newtons. So that's what I mean when I say it's an intelligent force. It does whatever it needs to oppose motion. Okay. Because of that, let's now talk about direction. So again, it's going to oppose motion. So it's going to go the opposite direction of motion. So if I'm pushing a box this way, then the friction is going to go this way. If I'm pushing a box this way, the friction is going to go this way. That's assuming the box is actually moving that direction, though. Because let's say I am pushing a box up a hill. Well, I'm trying to push it. It's currently sliding down this direction, and I'm just here trying to hold it up, and failing because the box is really heavy. So I'm trying to hold it up, but it's not working. It's still sliding down. In this case, friction is helping me because it's trying to oppose the box's motion downwards. Even though I'm pushing up, the box is moving down. So the relative motion is this direction. So friction goes this way. But if instead the box is moving this way, then friction is going to oppose my motion. It's going to make it harder. There's a few interesting cases with rolling motion that we're not going to talk about yet. I'll talk about in a future video, but friction is going to be expanded on more in the future. Okay, now that I actually talked about on an incline, that allows us to talk about one of the most important topics with this, which is friction on an incline. Now, at this point, you should know how to do basic incline plane problems. That is like if you have a box sliding down an incline plane, what's its velocity and stuff. Friction and other forces can be added into this to make it a tiny bit more complicated. The great thing is that it's almost all going to work the exact same as normal. The incline plane stuff is the exact same. Now you just have to consider one extra force to take into account to the motion. So typically, we say that if it was on a frictionless plane, the F is equal to mg sine theta. This is still true, except now we have a friction force to take into account too. I want you to remember what the formula for its for friction force was. Let's use kinetic friction right now because it's just easy to work with. Fk is equal to uk times Fn. When on a flat surface, Fn is typically equal to mg, but that's not always true. In this case, it's not true, because the Fn is this force here. Now, what do you think it is? I'll give you like 5 seconds to think of that, so. Okay. The Fn, in this case, is going to be mg cosine theta. Where I should say this angle is theta. And I could explain deeper about how to get this. I'm probably going to do an inclined plane video anyway, so I'll just explain it then. Either way though, so this is an important thing. Remember, the Fn isn't always equal to mg. In this case, it's equal to mg cosine theta. And the friction, all you have to know here is how to figure out the direction of it. And remember, that's just based off of the direction the block is trying to move. So if it's moving this way, friction's going this way. If it's moving this way, friction's going this way. Otherwise, that's all pretty typical stuff. I'm going to expand a bit more on this Fn stuff. So let's say I have a block, and now I put another block on top of it. Is the friction this block's experiencing from the ground the same as it was before this block was put on? If I'm trying to slide this way? The answer is no, because this block is pushing down on this block, which causes it to push harder on the floor, causing there to be more normal force. Okay. So now the last big idea there is to friction is what happens when we actually have these two objects on top of each other and I move the bottom one. If you try it yourself, you grab like a book and put another book on top of it and push it slowly, you notice that the top book moves along with it. So if I go here, this block, this is also going to move. That's because of the friction. The friction was causing this block to move. And you might be wondering, okay, wait, why is it causing this block to move this way? That makes no sense. That's because the relative motion between these two blocks is this block is going this direction. It's trying to move this way. So the this block is going to be pushing back this block this way. And due to Newton's third law, it's going to be moving itself this way. That's important to remember. Newton's third law. Every force has an equal and opposite reaction. Because of Newton's third law, it's going to be pushing this block back and this block forwards. So remember, this block is is experiencing a friction force and also giving one to this block over here. So when I'm calculating the friction on this block, on the bottom block, I have to consider both the fact that it has an increased normal force to calculate the friction with the ground, and I have to calculate the friction it's experiencing with the top block. So in this case, I would consider it to be like the friction force, I'm just going to do FF right now, is equal to the friction FF of, I'm going to say this is block A and this is block B, of AG, where G is the ground, plus the friction of AB. Again, that's like the last real major idea. There's a lot of other examples of friction. Like, if I were to take a paper and push it against a wall, I don't know why I actually did that in real life. I'm going to take this off my wall. The force holding it up is friction as a result of the normal force I'm applying onto it. Otherwise, yeah, that's really it. I'm going to move on to a short section where I solve problems about friction. Okay, now let's start solving some questions. This is the first question. What is the maximum tension of the rope attached to block 1? Both blocks are stationary. We have this situation. We have block 2 on top of block 1. Block 2 is attached to this wall. Block 1 is attached to this wall. And this rope here is pulling on block 1. And both of them aren't moving. They're not accelerating. Nothing's happening with them. And we're talking specifically this rope for block 1. And I didn't give like any variables and specifics right now. In an actual test, you'll likely see it with like actual values given. So like we might say this block has a mass of 3 kilograms. This block has a mass of 2 kilograms. I was too lazy to do that, to be honest. Instead, when we're going through this, basically we're talking about how you would go about solving one of these. And if you actually had it on test, you would have to plug in the values. Right now, we're not going to do that. I'm going to give you like 5-second countdown in my head to try. You can go pause it and you're going to try solving through this question if you had like actual values to plug in there. Right now, we're just going to work in things like M1, M2, mu S1, mu K2. Remember, mu is the coefficient of friction. Okay. So first off, we're going to make a force body diagram because, of course, we are. So it's stationary, so that means it's currently balanced right now. And we can start with the y. So right now there is the weight of its own gravity. So it's Fg. And also the force of this block here. It shouldn't be that big. Just make it like this big. Fa. To counteract it, the only force it has pushing upwards is the force it has against this ground. So that's Fn. A really big Fn, since there's another weight pushing down on it. Now to the right, it has Ft. And to the left, let's see, it has the friction of itself on the ground. And one more. That's going to be the friction from this block on top of it, because it's pointing this direction, so it's also rubbing against this block, and therefore this block is going to be applying a friction on it. Actually, I'll go write it as F21, just to make it more consistent how in this form. So these are the forces. We want to calculate Ft. And what we know is that since it's balanced, Ft equals F1g plus F21. So what we're going to do is plug in values for F1g and F21. And remember, since they're not moving, it has to be static friction that they experience. And static friction is less than or equal to mu s times mg. Well, not mg actually. That's it for most situations. It's actually equal to Fn. Most situations, Fn equals mg, but sometimes it's different. In fact, this is one case where it is different. And it's important to note this less than or equal to sign. That's why this question specifies maximum tension. That way we can just say it's equal to blank, because this is the limit of what it can be. And therefore that's the max. So we can say it's just equal to blank. So F1g should be the normal force experienced by block 1 times its coefficient of friction. And the normal force it's experiencing is equal to Fg plus Fa. So I'm just going to write Fn of block 1. I'll just write over here because I need more space. Fn of block 1 is equal to Fg plus Fa. And Fg is equal to m1 times g. And Fa is, this block pushing down on it, is equal to m2 times g. So that means that F1 on the ground is equal to mu s times m1g plus m2g. And typically, they're going to tell you what the mu s value is. Sometimes the mu's between the different surfaces are different. Sometimes they're the same. This case, we're just going to say they're the same because I'm lazy and don't want to have to make them different. It also doesn't make the question that much harder. So, and next is F21. So that means it's the friction experienced by this block here. So then that means it's equal to mu s times the normal force of this block. So Fn2. N2 is just, for this one, if we were to make a little force by diagram for it, the forces acting on it are tension this way, friction this way, actually, yeah, I just had to think of it for a second just to make sure. And Fg this way, and normal force this way. Now it is important to note whether or not it should be static or kinetic. Since the blocks haven't moved yet, it's static and the force is higher. As soon as one of the blocks slides, though, the friction is gonna drop, and because it's not gonna be kinetic friction, and they're gonna pull a lot easier. Okay. And Fn is equal to Fg in this case. So that's how we prove. That's how we find this Fn2 value. It's going to be equal to its Fg. Since this is just equal to mu s times m2g. So you can say Ft equals mu s times m1g plus m2g plus mu s times m2g. Okay. That's the first question. And from here, we're going to solve, I think, 2 more. So yeah, let's go on to the next one. Okay, now in this question, I was going to do another one, but then I realized that this question, I think, covers like the bigger main topics, and that's why we're going to do this one. Okay, you have a block on top of a block on an incline. What is the fast acceleration the bottom block can have before the top block slips off? And so we have this system right here. Let's pretend there's like a rope pulling this one up or something. Either way, it's accelerating faster and faster. Asking what's the maximum acceleration before this top block slips off. So I'm gonna give you guys like a second to think of how we would go for that. Okay. So what we would do is see how high its static friction can get, because this block's being held on by static friction. It hasn't started to move yet. The bottom block, well, actually, it has started to move when this block moves. But remember, it's all about relative motion, motion between this block and this block. If this block is accelerating at 5 meters per second, and this block is also accelerating at 5 meters per second, then there's no motion between the two of them. It's similar to the situation if you put your two hands together and push them both forwards. There's no relative motion between the two of them. And the static friction is going to increase in order to prevent any relative motion from happening between the two of them. But once they begin accelerating too fast for the static friction to keep up, then it's going to slip off. And we're trying to find when it's accelerating too fast or to slip off. So first off, what do you know about something on an incline? What's its natural acceleration? The natural acceleration of something on an incline is a equals g sine theta, where this angle is theta. And the force that's experiencing downwards is therefore mg sine theta. So this block is experiencing a force this way equal to mg sine theta. Now we have to find what its maximum acceleration this direction can be in order to calculate its friction. And so, remember, Fs is equal to, actually not equal to, but it's less than or equal to mu s Fn, and Fs max equals mu s Fn. Means it's max equal to mu s Fn. And since we're looking for the maximum acceleration, what we would look for is this value. And so we have to find what Fn is equal to. So that's this value up here. This one is one you should remember. Fn is, in this case, is equal to mg cosine of theta. This is one that you should simply remember. If you don't understand it though, it is using the same, almost the same exact explanation you used to find this mg sine theta value. Because remember, this is the original g value, and then we turn it into two components. This component is equal to mg sine theta, because it's mg times the sine of theta. And this component is therefore equal to mg cosine theta. So this component here equals mg cosine theta. Okay, so that means that the Fs max equals mu s times mg cosine of theta. So that means that the forces acting on this block will be mg cosine theta, or mu s cosine theta, minus mg sine theta. And therefore its maximum acceleration, because F equals ma, is a equals mu s g cosine theta minus g sine theta. Okay, and that gets together both slipping and friction on an incline. I think that's the last big question I will answer in this video. Hopefully this was helpful to you. If you have any more questions, please just comment them below. I'll do my best to help out however I can. And my next video, I plan for it to. I was wondering if I should cover gravity, because I think gravity is actually one of the easier units after you just look over all the values again. And it's not very complex. If you guys do want me to cover gravity, then please do say so. I don't plan doing it at the moment though. In my next video, I do plan doing is probably going to be about resistive forces. I think resistive forces is a good one. And for that one, I'm going to specifically cover how to derive the velocity of something falling with air resistance. That's something I know can be a bit confusing at first. And after that, I'm planning on covering circular motion. And those are going to be the topics I cover for this unit. That's at least my plan. If anyone wants to cover something else, please just do say so. And so yeah, I'll see you guys next time.